And so here are Euler's relationships. You're going to see a lot of complex exponentials with DTFTs. And so just as a reminder of what they are, e to the j theta is cosine of theta plus j times sine theta. So it has a real part, that is its cosine of whatever you put in here, and an imaginary part of what its sine is. You can graph this. If you want to find what e to the j theta is for any value theta, it has a real part, it has an imaginary part, and the answer lives along this unit circle. And in fact, if you put in any value theta for it, it's as if you rotated a line along theta, where this is 1, and this is j, and this is -1, and this is minus j, and this is the point of e to the j theta. So if you're only interested in the real part, the cosine part, you can see for theta equals 0, it's 1. As you increase theta, the part that's projected onto the real axis gets smaller until it's 0 when theta is pi over 2. It's -1 when it's pi. It's 0 when it's 3 pi over 2. And it's back to 1 when it's 2 pi. So just as an example of this, if you wanted to evaluate e to the j pi, that's just this example here in purple, in orange, is just pi over here, and so it's -1, and you can see that. Similarly, e to the j pi over 2 would be this vertical line up, which would just be j. It's pretty crazy when you think about it, how a irrational, non-algebraic number like e raised to the imaginary number, the square root of 2, times another irrational, non-algebraic number like pi is equal to exactly -1. Okay, so this is his first relationship. His second relationship is that you can create a cosine of theta with two complex exponentials, one e to the j theta and the other plus e to the minus j theta. And similarly, you can combine them to find a sine of theta if it's 1 over j2 times e to the j theta minus e to the minus j theta. So the things I want you to realize with a sine is that there's a j out here and it's a minus sign. These are Euler's relationships. And they're really handy when you get, they're really handy to combine odd-looking complex exponentials. So for instance, let's say that you had something that looked like e to the j pi over 4n minus e to the minus j pi over 4n. So what I would do is I would say this, I can see that there's clearly something going on here because these look almost the same. There's just a negative sign here. We've got a minus sign between these two complex exponentials, so we're going to have to convert it into something that looks like sine. But the problem is that there's no 1 over j2 here. So the only way that we can compensate for that is to pretend there's a 1 over j2 here. I'm going to write this actually in a different color to make it clear what I'm doing. We're going to pretend that there's a 1 over j2 over here. And since there's really not, I'm going to have to multiply the whole thing by j2. So those j2's cancel. So I've clearly not changed what my overall expression is. But now inside here, it looks exactly like what we've got for sine. And so I can just replace everything inside the parentheses with our sine of j theta. So it's j of pi over 4n. And then I have to multiply it by j2. Okay, if there are no questions, what I want you to get out of the Euler's relationship portion is that if you see the summation of two complex exponentials, if they've got the same power, you can probably use Euler's relationship to convert them into a simple cosine or a sine. And if it's a subtraction between two complex exponentials, it'll convert into a sine with a little bit of algebra. If it's a sum of two complex exponentials of opposite powers, you can convert it into a cosine.